In this video, we're going to discuss another fundamental principle of counting, the multiplication principle. And I'm going to introduce the idea with an example. So suppose you're planning a trip to Machosen, but you would like to go through Langford on the way. So Google Maps gives you 3 routes, each with the same time estimate from Victoria to Langford, and then 2 different routes from Langford to Machosen. How many different ways could you go all the way to Machosen through Langford? So that's what we're wondering. So we can kind of draw a picture here. So say we're in Victoria. We want to get to Langford, and there's 3 available routes. I'm going to call them L1, L2, and L3. Now, once we've picked one of these routes, we still have 2 options to get to Machosen. So we could take M1 or M2, depending on which route we take to Langford. So if you see, if you follow one of these paths, say from the beginning to the end, it gives you one route. So this would be that we took L3 and then we took M1. If we take a different one, so maybe we take L1 and then M2, that would be along this route. So each of these different paths is a different route from Victoria to Machosen that goes through Langford. So now we just need to count, well, how many endings are there? Because each ending corresponds to a different way. So we see that there's 6 routes. There are 6 different routes that you could take. Now notice that 6 is 3 times 2. Now this is called the multiplication principle, so you might be expecting some sort of multiplying to be happening here. 3 was the options from Victoria to Langford, and 2 was the number of options from Langford to Machosen. So in order to get from Victoria to Machosen, we needed to first pick a route to Langford, and then from there pick a route to Machosen. So all we had to do was multiply those 2 number of options to get our total number of ways to do the complete task. This is the idea behind the multiplication principle. So let's state it more formally. Suppose that a task is composed of 2 consecutive choices. If choice 1 can be performed in m ways, and choice 2 can be performed in n ways, then we can complete the full task in m times n ways. So let's see another example. So here there's 2 theaters, Theater A and Theater B. They're each showing the same 4 movies. So you want to go to a movie tonight. In how many ways can you select which one to go to? So our tasks that we need to compute, we need to select a theater, and then we need to select a movie. So, to select a theater, we only have 2 options, and to select a movie, we have 4 options. So, the total number of ways we can see a movie is 2 times 4, so 8. There's 8 different ways. This can be generalized to more choices as well. So suppose a task consists of t consecutive choices. Choice 1, you have m1 different ways to do it. For choice 2, you can perform it in m2 different ways. Choice 3, m3 ways, and so forth. So choice t is going to have m sub t ways. Because we have to do all of these tasks, one after the other, to complete our goal, the complete task can be performed in M1 times M2 times M3, and we just keep multiplying until we get to MT. So we multiply all the number of ways together. Now my note here, because later on in the course we're going to have times where we need to add instead of multiply, I'm going to try to emphasize what we should be looking for in order to know to multiply things. So you want to multiply if you find yourself saying and then, okay, or something similar. So to go back up for a movie example, we needed to select a theater and then we needed to also select a movie in order to know where we're going to go. So you had to do both things. So you're doing one and then another. So if you keep saying and then when you're describing the problem, it means you have to do all those things. So you want to multiply them. Okay, let's do one big example here. Now a note at the beginning, when we use the word word in mathematics, we just mean a string of letters, so it doesn't have to be a real English word. So keep that in mind when you're doing any problem where they ask you for how many words there are. So first of all, it asks how many three-letter words are there? So I'm going to write this one out a bit formally. Okay, so what are our tasks? So we need to know, what do we need to decide? Well, if it's a three-letter word, okay, we need to pick 3 letters to go into it. So we're going to have to select the first letter, so letter 1, and then we're going to have to select letter 2, and then we're going to have to select letter 3. So how many options are there? Okay, well, the English alphabet, which is what we're using, has 26 different letters. Okay, so when we select a letter, we're going to have 26 options. So for letter 1, obviously there's 26 options. We haven't picked anything yet. Now for letter 2, it doesn't say anything about repetition. Okay, so that means we should assume we can have repetition. So we could pick the same letter again. So for instance, the word A is valid. So that means we're going to have 26 options again for both of our other tasks. Okay, so that means that the total number is going to be 26 times 26 times 26, which is 26 cubed, which, if you want the number, is 17,576. Now, this is a lot of writing. Okay, normally we are lazy and we don't do that, but we still want to show our work. So what we might do instead is have 3 spaces, okay, 1 for each letter, and then underneath write what we're doing. Okay, so this one, the first space is going to be letter 1, the second space is going to be letter 2, and the third space is going to be letter 3. And then I would have 26 options for each, and that would be enough to show my work for what I was doing. I would understand what happened there. So you're saying to choose letter 1, okay, here, there's 26 options. To choose letter 2, also 26 options. Okay, so for the rest of them, I'm going to start writing it with this sort of shorthand notation. Okay, how many 3-letter words are there if the last letter must be a vowel? Now, to try and use our set theory, I'm going to define some notation. So let's let V be the set of 3-letter words that end in a vowel. So then what we're looking for is the number of things in V. And obviously we don't want to write them all out because there's actually lots of them. So the last letter must be a vowel. So we could use what we did up above. So I still need 3 letters. So I still have to pick letter 1, letter 2, and letter 3. Okay, now letter 3 has to be a vowel. And the vowels are A, E, I, O, and U. Okay, so now we want to go through. So let's start at letter 1 maybe. Okay, so how many options are there for letter 1? Well, this can be any letter, so there's still 26 options. What about letter 2? We're allowed repeats. It doesn't say we're not. Okay, so we can repeat the letter. So we still have 26 options. And now in the last letter, we can only pick one of these options. So, and it doesn't matter if we've already picked it. Okay, so that we're going to have 5 options in that spot because there's 5 vowels. And if you compute that, you multiply all those together, you get 3,380 different 3-letter words that end in a vowel. Okay, let's try another one. So how many 3-letter words have no repeated letters? So again, I'm going to call this one R for the set of 3-letter words with no repeats. Okay, so now we can't pick the same letter anymore. So I'm looking for the number of things in R. Again, it's going to be 3 letters. So I have 3 spots. I have to make 3 choices. Letter 1, letter 2, and letter 3. So suppose we start on the left-hand side. How many ways are there to pick the first letter? Well, we haven't picked anything, so there's going to be 26 options. Now, what about for letter 2? So we can't pick what we picked in letter 1 because it needs to be something different. So I'm just going to make a note here. So this one can't be the same. So it can't be whatever I picked there. Now, obviously, I don't know what I picked there, but I know I picked 1 letter only. Okay, so I put 1 letter in the first spot. So even though I don't know exactly which letter I put there, I can just remove it, whatever it was, and I'm going to be left with 25 options for letter 2. Okay, so similarly, letter 3 can't be either of those, whatever we picked in the first 2 spots, so I'm down to 24 options for letter 3. And if you multiply these up, it's 15,600 different words with no repeated letters. Okay, slightly harder example. How many 3-letter words have no repeated letters and end in a vowel? So this means that they're in set R, and this end in a vowel means they're in set V. So what we're actually looking for here is the number of words in R intersect V. Okay, now again, we have 3 letters. So I'm going to start with my 3 spots. Okay, now this one has to be a vowel. So we'll just make a note of that. Now, this is a tough one. So I'm going to write on the side over here. Let's just take a space. What happens if we start, so I mean you might assume this is going to be wrong. So what happens if we start on the left? Okay, so let's say we start on the left, so we have 26 options. Okay, now letter 2, there's going to be 25 options because I can't use repeats. Now what about for letter 3? So it has to be a vowel, and it can't be whatever I've picked earlier. So the problem that happens is we don't know if we chose vowels here or not. Okay, if we did, the number of options for the last spot is going to be reduced. But if we didn't, I'm still going to have 5. So that means that this spot depends on our previous choices. Okay, so that's a bad thing. So that actually means we can't finish this way. So what if we try again? So another thing I might see is, okay, let's get rid of the vowels. So instead of 26 options at the beginning, I'm only going to have 21. And then the second one obviously can't be the whatever I picked in the first one. And now I definitely have 5 choices at the end. So the problem here is that we never get words that start with vowels because we eliminated them. So you can see, so we took them all out, but then we're never going to get the vowels at the beginning. Okay, so we're having some problems here. Now, one thing I'm going to recommend when you're doing it this way is sometimes it's easy. You don't have to go left to right. I mean, it so happens that in the previous 3 examples we did. But there's nothing saying that we have to pick the first letter first. So it actually turns out sometimes to be helpful if you pick the hardest letter to fill first. So letter 3 here is the most restricted. Okay, so let's try and pick that one first. So because we haven't picked anything yet, we know that there's 5 options for that. Okay, all the vowels are still available. Now I'm going to go up to letter 1. Okay, it doesn't matter which one I go to now, but I'm going to go to letter 1. So I know that it can't be whatever I picked, whatever vowel I picked, but it could be anything else. So I'm going to have 25 options for that spot. Okay, so similarly in the middle spot, I can't be either of the things I've just picked, so I'm going to have 24 options. So the number of words in R intersect V is going to be 3,000. Okay, so that one's a bit tricky. The hardest part here is that you're so used to, I tried to lull you into a sense of, oh, we always go left to right. So you get that in your head, and it's difficult to realize that you can't do it that way. So you need to abandon that strategy and try something different. And here, all we had to do was start in a different place. Okay, but this can be really hard to do. Once you get set on an idea, it's hard to abandon it. So sometimes you're going to have to, and that's totally fine. Okay, not everything you come up with at the beginning is gonna work. Okay, one more example. This one's a bit different. So how many 3-letter words have no repeated letters, so they're in R, or they end in a vowel, so they're in V, or both? Okay, this is the union. So what we're looking for is the number of words in R union V. Now notice up above, we've computed the number of things in V. We've also computed the number of things in R, and we've computed the number of things in R intersect V. These are all the pieces we need if we use the principle of inclusion exclusion. So we've actually done all the work for this if we want to use the principle of inclusion exclusion. Okay, so this is going to be the fastest way, given what we've done. Because of the or, it's usually easier to count when you know what's happening. So the unions are often easiest to do with the principle of inclusion exclusion, but not to say that you can't do it another way. There definitely is. So the number of things in R, we said, was 15,600. The number of things in V was 3,380, and the intersection had 3,000. So if we compute that, we're going to get 15,980 in this set. So that's a brief intro to multiplication principle. I highly recommend you do lots of practice on this in the future.